Welcome to the Resource Allocation Decision Tool, Help Video 2.4. My name is Terry Haines. The focus of this video is key to success number 4 when using research evidence to inform resource allocation decision making. The focus is to understand meta-analyses and standardized effect sizes. In our previous video, we examined the results of a single study. But what do we do if there's more than one study? Meta-analysis is a statistical approach for combining the results of many studies of the same or very similar question. This usually results in having 95% confidence intervals of the treatment effect estimate that are more narrow or precise. Here we can see a graph representing the results of our previous study, comparing coffee drinking to water drinking on time to run 100 meters. Our original study is visible at the top of this forest plot with the difference between groups of 1.4 seconds. We've now repeated this experiment 2 more times with different groups of people. The results have been a 2.4 second difference or a 0.4 second difference between the two groups, but the 95% confidence intervals for each study has remained the same. A meta-analysis has been performed and can be seen with the blue diamond at the bottom of this graph. Here the point estimate of the treatment effect is the same as our original study, a 1.4 second difference. However, you will now be able to see that the confidence intervals are much more narrow, going between -2.4 and -0.4 seconds. As the 95% confidence intervals of this pooled treatment effect estimate are completely to the left-hand side of the null value of 0, we have a statistically significant difference between our intervention and control conditions, which we didn't have in our original study. Again, this is because the 95% confidence intervals have shrunk. Now, it's possible that some of our studies we included in this analysis might have measured our outcome in different ways. One of our studies might have measured the outcome in minutes and not seconds. However, it's quite easy to convert minutes to seconds if you know that 1 minute equals 60 seconds. Often, however, it's not as easy as this to combine the results from multiple studies. For many health service delivery questions, the outcomes can be measured using different approaches, and no simple conversion formula like this exists. Let's look at another example. Does providing group therapy reduce symptoms of depression in depressed adults after 6 months? We're going to consider 2 studies that compare group therapy to a control condition. The first study measured the primary outcome using the Geriatric Depression Scale short form, which has 15 items and generates a score between 0 and 15. The second study measured the primary outcome using the Beck Depression Inventory version 2, which has 21 items and generates a score between 0 and 63. If we hypothetically run these 2 studies and see our results, we see that study 1, which used the Geriatric Depression Scale as its primary outcome, had an effect size of 1 point difference between the intervention and control groups in favour of the intervention using the GDS scale. However, the Beck Depression Inventory study had an 8-point difference using this scale's metrics. It's difficult, however, to understand exactly how these 2 studies relate to each other given they've measured their outcomes on different scales. Standardized effect sizes help us to resolve the situation. They allow us to make comparisons between studies that have used different tools to measure the same outcome. A standardized effect size equals the difference between group means divided by the standard deviation of the outcome. This standardized effect size has no units, so we can statistically combine the results from different studies. Now we see study 1 with a standardized effect size of 0.26 and study 2 with a standardized effect size of 0.91, leading to a pooled meta-analysis overall effect size of 0.62, which isn't quite statistically significant. Again, the 95% confidence interval of the effect size does cross the null value of 0. One advantage of using standardized effect sizes are that there are conventionally used descriptors of how important they are, sometimes referred to as Cohen's effect size descriptors. In our meta-analysis, we can see that study 1 had a somewhat small effect size, standardized effect size, I should say. That study 2 had a large standardized effect size, and that the overall pooled result was close to being a medium effect size. Standardized effect sizes cannot be used for some outcome measures, however. Some outcomes are binary or dichotomous, such as a success or failure, or if a person returned to work or did not return to work after a back injury. Some are count outcomes, for example, the number of adverse events that a patient experienced while in hospital. And some are ordinal outcomes, commonly seen in surveys where Likert scaled responses are used, such as the strongly agree to strongly disagree scaling. Now, ratio-based effect sizes can also be used in these situations. So, effect sizes such as odds ratios, relative risk, hazard ratios, or incident rate ratios may be able to be applied in these situations. And let's do it to our coffee versus water drinking example. Here we see the result when we look at the mean difference in time to run 100 meters between the two groups. However, another way that we could have analyzed our results would be to classify participants as yes or no in terms of whether they were able to run 100 meters in 12 seconds or less. If we compared the proportion of participants who could do this in each group, we might get an odds ratio. Here, using the data we presented earlier, we gain an odds ratio of 0.29, with a 95% confidence interval between 0.05 and 1.82. It's important to note, however, that the null value for a ratio-based effect size is not the same as for a standardized effect size. Even though the 95% confidence interval does not include the value 0, it is not a significant finding, because for a ratio-based effect size, the null value is actually the value 1. As we go to the left of screen, the values that you can see will get close to 0, but will never get lower than 0 and will never be negative numbers, and the numbers to the right of screen will get close to infinity. So the way you interpret the numerical value of a ratio-based effect size is quite different to how you interpret a standardized effect size. So, our key to success with using research in making resource allocation decisions is to make sure we know that meta-analyses help to combine results from many studies, and they do so by treating all the different studies as one big study, and that standardized effect sizes can be used to help compare outcomes across different studies. There are different ways, though, that effect sizes can be expressed, so it's important to understand how they are different and how they are interpreted.